Okay, everybody. This is 7.3. It's an exciting section because it helps you fill out your unit circle that I gave you in the 7.1 notes, if you saw it at the very end. And it lets us know where those actual coordinates come from. We're going to prove where the coordinates on the unit circle come from, which is so much better than just Googling a unit circle. Anybody could do that, right? We want to actually create these coordinates. And we're going to create these coordinates based off the unit circle and triangles. It's crazy, right? Everything's based on triangles. Okay, so we'll first start by finding the 6 trig values at pi over 4 radians or 45 degrees, since they are equivalent. And the way we do this is by creating an isosceles triangle. If you don't know what an isosceles triangle is, well, there's the definition. A triangle that has 2 equal sides and 2 equal angles. And since the triangle is isosceles, then sides A and B are equal and greater than 0, of course. Okay, so that's how we're going to start off. Let me see. Play with my room here. I'll do that. And is there a right triangle tool? I have no idea. Let me try. No. So I'll just draw my own. Okay. So we'll start with an isosceles right triangle. Where's your ink to shape? I should probably do that. My shapes are terrible. Yay, there we go. Look at that. Beautiful. Okay. Turn that off. And down below I have 45 degrees or pi over 4. I'll just put 45 degrees here. 45 degrees, we know that is 90, and this means the other angle must also be 45 degrees. Okay, so this is an isosceles triangle, so normally we would write this as base B, height A, hypotenuse C, but since A equals B, this means that this B becomes A, because the sides are equivalent. Okay, so that's what this is going to become. This becomes A. Okay, so now, in order to prove where those coordinates come from, we need to get C all in terms of A. And the way we're going to do that is by using the Pythagorean theorem. We're going to solve for C. So that's what we're going to say here. Solve for C. And we know that by Pythagorean theorem, it's A squared plus B squared equals C squared, but since this is an isosceles, this just becomes A squared plus A squared equal to C squared, which then becomes 2A squared equal to C squared, which then we square root. And then this just becomes A square root 2 equal to C. And don't worry about the plus or minus. We can't choose minus because we're talking about length. So you get A square root of 2. So this means that we will now replace this C with A square root of 2. And now, since we have the whole triangle in terms of A, let's go ahead and find the 6 trig ratios, which I think I put as a box down below. So, looking at our right triangle, we want to know what is the cosine of 45 degrees. What is the cosine of 45 degrees, which is the same as the cosine of pi over 4? Remember that 45 and pi over 4 are the same. So in order to do this, we need to know what is the ratio of cosine. And cosine puts adjacent over hypotenuse. So this puts A over A square root 2, where your a's will cancel and leave you with 1 over square root 2, which you rationalize as square root 2 over 2. Perfect. So this means that the cosine of 45 degrees is the numerical value of the square root of 2 over 2. Plug it in a calculator and you'll see that this is true. If you're doing degrees, make sure your calculator's in degrees. If you're doing radians, make sure your calculator's in radians. But the numerical value of cosine of 45 degrees is square root 2 over 2. Okay, now let's do the same for the sine of 45 degrees. And honestly, it doesn't matter which angle I'm calling on because we're getting the same ratios. So I'm just using this generic value in the corner. So now we'll do the sine of 45 degrees, which is opposite over hypotenuse, which gives us the same situation as cosine. A over a square root of 2, which would eventually become square root 2 over 2. Okay, now look at the triangle and let's figure out the remaining trig functions. And just like this, sine of 45 degrees is also the numerical value of square root 2 over 2. Then if we look at tangent, tangent of 45 puts opposite over adjacent. I can probably do that. How's that? Tangent puts opposite over adjacent, and a over a is 1. So this means that the tangent of 45 degrees is 1. Okay. Wonderful. Now let's find the reciprocal functions, which isn't hard because all we have to do is take the reciprocal of these numbers. All right. I did mix it up. My bad. The reciprocal of sine should go here because it's cosecant. So cosecant is a reciprocal function of sine. So that means you would just flip this as 2 over square root 2. And then you would rationalize, and that would become 2 root 2 over 2, which is just square root of 2, I think, right? Let me see. So I'm not lying. 2 root 2 over 2, and yeah, so that's just the square root of 2. And then same thing could be said here. The reciprocal of cosine is secant, and that's going to be the same situation as cosecant. You're going to get square root 2. And then guess what the reciprocal of 1 is? This is the only chart I got right. The reciprocal of 1 happens to be 1. I can leave that arrow there. Make it a prettier arrow. 1. Okay, and those are the 6 trig values. Those are actual values of the trig functions at 45 degrees or pi over 4 radians, which means we can fill out the coordinates for every pi over 4 around the unit circle. So before we do so, here's something very, very important to note. The trig values are based on a rectangular plane where we can relate a coordinate x, y to the trigonometric functions cosine and sine. So cosine always relates to the x values and sine always relates to y values. So cosine is always x, sine is always related to y. And the reasoning behind that, if I drew a quick sketch, if we have the coordinate plane or even a unit circle and drew my triangle anywhere, the base B and the height A will be is also known as x. And A, the height, is also known as y. And when you call on the angle, cosine of theta, we'll put the radius here as c, cosine of theta would put x over c. So cosine always relates to x. And sine of theta would put height over the hypotenuse c. So cosine relates to x and sine relates to y. That is the important note. And it doesn't go any other way. Cosine is always x, sine is always y. Okay. So now we can fill out our unit circle, and what we're going to do first is look at 45 degrees. And at 45 degrees, you will have the coordinates square root 2 over 2 over 2, square root 2 over 2. And now fill that out for every other pi over 4, but make sure you account for the positive and negative coordinates, quadrants. So if I move over here, in the second quadrant, all your x values are negative. So you would get negative square root 2 over 2, and your y values are positive, positive square root 2 over 2. Down below, in quadrant 3, at the next pi over 4 value, you would get, well, everything is negative, so you would get negative square root 2 over 2, negative square root 2 over 2. Am I writing that in the correct spots? I don't think so. Oh, that should go there. My bad. Negative square root 2 over 2, negative square root 2 over 2. And then over here at the last pi over 4 value in quadrant 4, x is positive. So you'll get square root 2 over 2, and y is negative. Negative square root of 2 over 2. And there you go. You're welcome. That's where the coordinates of pi over 4 come from, or 45 degrees. Using right triangles, the unit circle, all that good stuff. That's it. Now you don't have to do this triangle method anymore, but let's say you forgot. It's so easy to reference and make. Okay. So another important message is we are now calling on the unit circle to give us a value. So when I say, what is the cosine of 45 degrees? So when I say, if I look at it, if I say, what is the cosine of 45 degrees? You look on your unit circle, you look at 45 degrees, and you give me the x value of that coordinate, because cosine relates to x. And you would say, hey, cosine of 45 degrees is square root 2 over 2. And you would do the same for the rest of the trig functions. If I said, hey, what's the tangent of 45 degrees? You would look at your unit circle, and you would know that tangent puts sine over cosine. So in this case, tangent would put y over x. So tangent would put this coordinate over that coordinate, and square root of 2 over 2 over square root of 2 over 2, anything over itself is always 1. So once again, we say, hey, unit circle, what is the cosine of 45 degrees? And the unit circle goes, oh, man, that's square root of 2 over 2. So we are calling on the unit circle to give us a numerical output. That's what we're saying. So we take an angle, we plug it into the function, and we look at the unit circle and say, hey, that's where that value is. And that's how you work it. That's how we will work the unit circle from now on. We call on it to give us those values. Okay. So now, the next page, we will fill out the rest of the coordinates by using triangles again. Okay. Now we want to know what are the coordinates at 30 degrees and 60 degrees. Okay. So we can do this by making an equilateral triangle. And if you don't know what an equilateral triangle is, it's a triangle with 3 equal sides and 3 equal angles of 60 degrees. Now, can I draw an equilateral triangle? Probably not, but we're going to try our best. And that's not how you do it. And that's not how you do it. Back here. I don't know why it went there. And that's definitely not how you do it. Why do you do that, man? Ugh. There we go, there we go. That looks pretty equilateral to me. Don't worry, we're going to cut it in half anyways. Okay. So it says, let's go ahead and label all the sides the same thing because it's equilateral. So this is it. Oh, okay. This is A, that is A, and that is A. And then inside, 60 degrees or pi over 3 radians, same thing. 60, 60, 60. And now, to figure out those coordinates, what we're going to do is bisect our equilateral triangle right down the middle. And when we do that, my equilateral triangle becomes a right triangle. Well, you get 2 right triangles, and we only have to choose one. So I can ink to shape again, and we get a little better. There we go, much better. Okay, so now we get this new triangle where the angle in the left corner is now 60 degrees, but now the angle in the top corner, since we split it in half, is now 30 degrees. Oh, I'm still doing ink to shape. Although those degree symbols are coming out nice. All right, turn that off. 30 degrees, and we know this angle is still 90. So now one thing we know for sure is that the hypotenuse of this right triangle is still A. And then the base, since we cut it in half, is now A over 2. And since we bisected it, we have no idea what that is. So we're going to call it H or X or whatever letter you like. So now, just like on the last example, we had to get the triangle all in terms of A. So for this one, we are going to solve for H using Pythagorean theorem. A squared plus B squared equals C squared. And, well, here my base, well, my A should be that H, right? So that's going to become H squared plus my B value is that A over 2. So you get A over 2 squared, and my C value, my hypotenuse, is actually A. So you get A squared. Okay. Then make sure you square everything. This becomes A squared over 4 equal to A squared. We're solving for H. So move over that A squared over 4. A squared minus A squared over 4. And then combine them. And we'll move up here. And you'll get h squared equals, if you put this over 1 and get a common denominator of 4, you'll get 3a squared over 4, where if you take the square root, you'll get h equals a square root 3 over 2. Which means this is now going in for h. Because if we do that, this means we are now all in terms of a. Which means now we can go ahead and find these 6 trig ratios of 60 degrees and 30 degrees. Well, I guess I should say 30 degrees first, because that's what I wrote here. Okay, and I'll explain what's going on in this chart because it looks insane. And again, I messed up the reciprocals, my bad. Well, it's gonna be even worse now. So that should go there, and that should go there. But when we get there, I mean, once you understand the reciprocal functions, you should be fine. Okay, so first up is finding the cosine of 30 degrees or pi over 6 radians. Those are equivalent. Okay, so here at 30 degrees, if we want the cosine of 30 degrees, it puts the adjacent side over the hypotenuse. So this means down below, I'll just do the side work down here, you put the adjacent side of a square root 3 over 2 over a. If I zoom in, I can actually write this better. A square root 3 over 2 over a. Then you multiply by the reciprocal of this a, giving me a square root 3 over 2 times 1 over a. Your a's will cancel, and you'll get square root 3 over 2. And that's what goes right here. Square root 3 over 2. So the cosine of 30 degrees is square root 3 over 2. Which now means that is also the same value for the sine of 60 degrees. And how do we know that? One, you can reference the triangle above, or two, you can reference complementary angle theorem that we did in 7.2. Because remember, cosine of theta is equal to the sine of 90 minus theta. So cosine of 30 degrees is equal to the sine of 60 degrees. So by complementary angle theorem, it makes sense to say that if cosine of 30 is square root 3 over 2, then so is the sine of 60. That's all there is to it. That's it. All I'm using is complementary angle theorem. If that doesn't make sense, then reference your triangle and say, well, the sine of 60 puts opposite over hypotenuse, which is what we have here. A square root 3 over 2 over a, and we get the same exact value. So you can reference the triangle, you can use complementary angle theorem, which is faster, and get the answer. Undo, 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 and erase all of this. I'll put a disclaimer up here. Using complementary angle theorem. I'm using a cat. Okay. All right, which means let's find the other 5 trig functions. Sine of 30 degrees. So we're still referencing this angle, and sine of 30 puts opposite over hypotenuse. A over 2 over a, which is what we'll write here. A over 2 over a, multiply by the reciprocal, which is 1 over a. Your a's cancel, and you get 1/2. which goes right there. Can't win today. Come on. There we go. Which also means by complementary angle theorem or the triangle above, cosine of 60, sine's cofunction and complementary angle with that cofunction is also 1/2. Okay, and then tangent of 30 degrees is next. Tangent of 30 degrees puts opposite over adjacent. A over 2 over a squared root 3 over 2. A over 2 over a squared root 3 over 2 multiplied by the reciprocal 2 over a square root 3, and you get your a's cancel, your 2's cancel, you get 1 over the square root of 3, which rationalizing gives you square root 3 over 3. And there it is. Which means the next 3 trig functions are going to be very easy to find. Okay. So for the first one, we want, well, we have cosecant of 30, which means that cosecant of 30 is the reciprocal of sine, which means that if sine of 30 is 1/2, then cosecant of 30 must be 2. So yeah, we can still do that. That's fine. Don't take it as that going to, I'll just say, there we go. Okay. Which means the complementary angle, secant of 60, is also 2. And then do it here. Secant of 30, secant is the reciprocal of cosine. And if cosine is square root 3 over 2, this means that we'll have 2 over square root 3, which gives us 2 root 3 over 3. So that goes right there. So secant of 30 is 2 root 3 over 3, which means cosecant of 60 by complementary angle theorem or the triangle above is 2 square root 3 over 3. And then the one I didn't mess up, when I say mess up, I just didn't put them in the right place. The reciprocals are right, it's just they didn't line up correctly. So it's not a mess up, it's just a mess up. Okay. And then tangent of 30 and cotangent of 30 are reciprocals of each other. So if tangent of 30 is square root of 3 over 3, this means cotangent is the reciprocal. But cheat code time. If this is tangent, step 1 back, and you get 1 over the square root of 3. Flip that, and you just get that cotangent of 30 is square root 3, or tangent of 60 is the square root of 3. There it is. Look at that. How fun, right? Okay. Which means now I can fill in my unit circle at 30 degrees and 60 degrees. So here, cosine at 30 is square root 3 over 2, and sine at 30 is 1/2. So that's what we're going to fill in. Cosine at 30 is square root 3 over 2, and sine at 30 is 1/2. Which means just flip them, and cosine at 60 is 1/2, and sine at 60 is square root 3 over 2. Now, do not mess these coordinates up. These are the official coordinates of your unit circle. And they come from right triangles. And people always wonder, how can I memorize these? I'm like, well, simple. First off, all the denominators are 2. And second, look at the countdown. 1, 2, 3. 1, 2, 3. Look at that. But if you really, really want to remember it, just tattoo it on your forearm. That's all you have to do. Okay. And those are the coordinates of the unit circle, and just fill them out at all the other pi over 3 and pi over 6s. I'll leave that up to you guys. I want to save time on this video. I mean, it wouldn't take me long. I'll fill it out later, but you get it. The only coordinate we're missing is the actual radius of the unit circle, which is 1. So if you look in the far right, you're going to get 1, oh my goodness, 1, 0. Then the very top, 0, 1. At the very left, -1, 0. And at the bottom, 0, -1. There we go. That's it. We can't mess it up. These are the official coordinates of the unit circle, and they come from right triangles splitting a equilateral triangle in half. And there you go. Now, once again, just to repeat it, cosine always belongs with x, and sine always belongs with y, and we are calling on the unit circle now. So from now on, after this lesson, during the lesson, right now, the unit circle is your best friend. Fill it out, print it out, tattoo it, put it on your fridge, put it above your computer when you're taking a test. You should be having breakfast with it, lunch and dinner. The unit circle is now your best friend the rest of this class. And it should be when you get to calculus and Cal 2. When you get to Cal 1, and if I say, what's the sine of 45 degrees? And if you stare at me blank for 2 seconds, get out of my class, okay? But then come back in, we'll go over it. All right. Okay, so now, referencing the unit circle above, here's the next exercise. We want to find exact values of trig functions referencing the unit circle. So let me see if I can drag this guy down here. Let me see. Nope, nope, stop it. I'll lasso it. How's that? This whole thing. There you go. You're coming down with me. Let's go. Let's go. Come down the screen. Let's go. I'll even collide it with this page. How's that? Okay. So this is how it's going to work. So I say, for the first one, it says sine of 45 times the tangent of 45. So we reference the unit circle. First, we look at the sine of 45 degrees. The sine of 45 degrees, here's 45, and sine outputs the y values. So we should put square root of 2 over 2. So that's first. So we get that that turns into square root of 2 over 2. That's what it turns into, nothing else. Sine of 45 degrees is square root of 2 over 2. Times the tangent of 45 degrees. Tangent of 45 degrees, so we look at it at 45 degrees, tangent puts y over x. Tangent puts y over x, meaning square root of 2 over 2 over itself is 1. So the tangent of 45 degrees is 1. So this becomes 1. So that's what tangent becomes. And square root of 2 over 2 times 1 is just square root of 2 over 2. That's it. We call in the unit circle to give us values. Okay. The secant of pi over 4 is next. I think I can, it looks pretty good from there. Okay, it does. Okay, so the secant of pi over 4. This means we look at pi over 4 and we have to think of reciprocal functions, the identities. Secant is the reciprocal of cosine. And what variable does cosine relate to on the unit circle and coordinate plane? Cosine relates to x. So this means the cosecant of pi over 4 is going to become, let me see, I have more room here. I'll write it out. So yes, so this becomes, and what you're going to do is take that coordinate, and since it's the reciprocal function, you're going to flip it. You're going to get 2 over square root 2. That's what that becomes. Times the cotangent of pi over 4. The cotangent of pi over 4. Well, once again, reference pi over 4. And cotangent is the reciprocal of tangent. So cotangent puts x over y. And we're stuck at a similar situation above. Square root of 2 over 2 over itself is still 1. So the cotangent of pi over 4 becomes 1. And we are left with 2 over the square root of 2, but we can't leave it like that. You must rationalize. So our answer just becomes the square root of 2. That's it. This is just us calling on a unit circle. That's all this exercise is about. Can I get away with that? Yes. Okay. Let's do it again. 4 times the cosine of 45 degrees. All right. 4 times, and cosine of 45 degrees would call on this angle, and cosine relates to x, so you would output square root 2 over 2. So that would give you square root 2 over 2. Minus 2 times the sine of 45 degrees. So once again, if you follow that arrow, sine of 45 degrees references 45 degrees, which then would call on the y value of that coordinate, which is also square root 2 over 2. And all we have to do is clean it up. I wrote really big, so I probably want to erase that. One moment. There it is, and then reduce. That becomes a 1, that becomes a 2. Those 2's cancel, that becomes a 1. And we end up getting 2 square root 2 minus the square root of 2, which also gives me square root of 2. Not bad, guys. Just know how to call in the unit circle. That's it. Sine of 45 degrees. Same thing. We've done this already. Look at the above. 45 degrees is square root 2 over 2. We do have a new one. Cosine of 30 says, hey, look at 30 degrees. What is the x value at 30 degrees? Because that's what it says. Cosine at 30 degrees wants the x value at 30 degrees. So we would have square root 3 over 2. And just multiply. You get square root 6 over 4. That's it. Tangent of pi over 4. Well, what does that become? Reference pi over 4. And tangent at pi over 4, remember tangent puts y over x. So tangent puts y over x, and anything over itself, that coordinate over itself is 1. So that would become 1. One minus, and then you have the sine of pi over 3. Reference pi over 3, and sine only calls on the y value. So you would output square root 3 over 2. Okay, and then there's not much you can do if, because that's actually an answer to me, but my math lab might make you put it together as a fraction, which is not bad. You just put 1 over 1, get a common denominator of 2, and your answer is 2 minus square root 3 over 2. That's what that becomes. Okay, last one. Well, for this part. Tangent squared of pi over 6. So what this means is reference the angle pi over 6, and tangent puts y over x. So we have a little bit of work for us to do. 1/2 over the square root of 3 over 2. So I'll write that down. And I have to put in parentheses. 1/2 over square root 3 over 2 squared plus. All right, we called on that. The sine squared of pi over 4. Oh, we don't even need a reference unit circle anymore. We know what sine of pi over 4 is. Sine of pi over 4 is square root 2 over 2, and we're squaring it. That's it. And now, I mean, we have to clean it up, of course. So zooming in, I'm going to rewrite it because it's very messy. 1/2 over square root of 3 over 2. Plus square root 2 over 2 squared. And inside here, you have to multiply by the reciprocal before moving forward. And you'd get 1/2 times 2 over the square root of 3 squared. Plus, over here, if you square that, you'd get 2 over 4. Over here, your 2's cancel, and you're left with 1 over the square root of 3 squared plus 1/2. Square that, and you get 1 over 3 plus 1/2. Because then, yeah, because you get 3 over 9, 1/3, and 1/3 plus 1/2 should give me 5 over 6. And there it is, y'all. That's how you call on the unit circle. And then you just algebraically evaluate it, simplify it. That's it. Okay. I think I could leave the unit circle there. That's fine. Okay. Moving on. Next is calculator work. Okay. This one's easy. Just plug these numbers in a calculator. So do I still have that? Let me see. You come here. You come here. Close that. And there we go. All right. So first important thing to notice is that when you type these in the calculator, make sure if it says degrees, you are in degree mode. And it is simple as typing the mode button. So up, I have the graphing calculator up. If you have this blue calculator up that I have on camera, there is a mode button. If you click mode, you can see degrees, radians, gradients. So for this, for 1 and 2, we need to enter on degrees, and then you can type in your functions. On the graphing calculator, hit mode, and go down and move over to degree, hit enter, and then quit, and we're ready to go. Okay, cosine of 48 degrees. Type cosine, type in 48, hit enter. And we'll go 3 decimal places. There it is. Cosine of 48 degrees is 0.669. That's its numerical value. Okay. And then cosecant of 21 degrees. So notice how this calculator and your blue calculator do not have cosecant. This is where reciprocal identities comes in handy. Remember, the reciprocal of cosecant is 1 over sine. So to type this in your calculator, you're going to have to write it as 1 divide the sine of 21. So I'll just type it in here. 1 divide the sine of 21. That's it. And hit enter. That's the same as cosecant. And you get 2.790. 3 decimal places. Sure. Okay. Now notice the last one, there is no degree symbol, which means we need to switch back to radians. So mode, down, down, click on radians, second quit, and we're typing in the tangent of pi over 12. So I'll do tangent. I'll find my pi button wherever it's at. There you are. Second up arrow, pi, divide 12. That's it. Simple as that. Enter, and you get 0.268 is the numerical value in radians of tangent of pi over 12. There you go. And that's how you use your calculator. Clean my pen. Almost there. Okay. Okay, on our way. So there's that, and then next is word problems, and we're out of here. 3 more problems, okay? Finding the width of a river. A surveyor can measure the width of a river by setting up a transit at point C on one side of the river and taking a sighting point A on the other side. After turning through an angle of 90 degrees at C, the surveyor walks a distance of 200 meters to point B. Using the transit at B, the angle theta is measured and found to be 20 degrees. What is the width of the river rounded to the nearest meter? All right. Diagrams are always important. So first up is me drawing a river. And then let's read it again. And it says that, let's see. He sets up a transit at point C on one side of a river. So we'll say here is C, right? Here's point C. And then he takes a sighting at point A on the other side. And then after turning through an angle of 90 degrees at C, the surveyor walks a distance of 200 meters to point B. So maybe I should switch these, hang on. This will be A, This will be C. So the surveyor's looking that way, and then he turns an angle of 90 degrees and walks that way to point B. So he walks 200 meters to point B. Okay, the angle theta is measured and found to be 20 degrees. What is the width of the river? Rounded to the nearest meter. So using the transit at B, the angle is measured and found to be 20 degrees. Okay, so here's what we have. So we know the distance from C to B is 200 meters. What we're trying to find is the width of the river, which we'll call X. And what we know is that when the surveyor used the transit at B, the angle measured and found was to be 20 degrees. So from A to B, this angle was found to be 20 degrees. Okay. So all we need to know is what is the length of the river in meters. So we need to know which trig function, based off of this angle's location, will give us that value of X. So think of the trig functions and their ratios. So if I said the sine of 20 degrees, the sine of 20 would put opposite over hypotenuse. Well, there's something we don't know. We don't know the hypotenuse. So is that going to work? No. So that is out. And then, if we said the cosine of 20 degrees, cosine puts the adjacent side over the hypotenuse. Is that going to work out? No, because once again, we don't have any idea what the length of the hypotenuse is. So cosine's not going to work out. But then we say, what about the tangent of 20 degrees? So we will make our way through all 6 to figure out which one works. And the tangent of 20 degrees puts the opposite side over the adjacent side. It puts X over 200 meters. Is this going to work out? And that answer is yes, because it can help us solve for X. All we have to do to solve for X is multiply this 200 to the left side. So once again, so I'm not writing too big, let me go ahead and erase this. And we'll get tangent of 20 degrees is X over 200 meters, which means if you multiply that 200 meters to the left side, you'll get 200 meters times the tangent of 20 degrees. And make sure to switch your calculator back to degrees. I think we left it off on radians, right? We left it off on radians. And this means that mode, I need to go back to degrees and second quit, and I'll say 200 times the tangent of 20 degrees, and we'll get that the width of the river is 72.79 meters. That's it. So for these word problems, sometimes tangent is the best function to use, but it all depends on the information you have and the ratios you're working with. Okay, cool. Next word problem. find the height of a cloud. Meteorologists find the height of a cloud using an instrument. Oh, I spelled that wrong. Instrument called a ceilometer. Might not even be saying that right. Ceilometer. A ceilometer or ceilometer, probably ceilometer, I don't know, consists of a light projector that directs a vertical light beam onto the cloud base and a light detector that scans the cloud to detect the light beam. On December 8, 2019, at Midway Airport in Chicago, a ceilometer was employed to find the height of a cloud cover. It was set up with its light detector 300 feet from its light projector. If the angle of elevation from the light detector to the base of the cloud was 75 degrees, what was the height of the cloud cover? Oh, what? Okay, so some definitions real fast. Whenever you see the words angle of elevation, this means that whoever's surveying or making these crazy problems is looking up. So the angle is always at the base of the triangle. If it's an angle of depression, then this person is looking down, and that angle is at the top of the triangle. So those are just some words to look out for and how you set up your triangles. Okay. So for this one, let's see. So a ceilometer was employed if it was set up with its light detector 300 feet from its light projector. So here's my light detector all the way to my light projector. So light detector, light projector, and this is 300 feet. The angle of elevation from the light detector to the base of the cloud was 75 degrees. So this means that my light detector hit this cloud. We want an orange cloud at 75 degrees. So this angle in here is 75 degrees because it's an angle of elevation. We're looking up at the cloud. Okay. And we want to know what was the height of the cloud cover. So again, that's going to be x. And now, once again, what trig function would be best to solve for this? And if you said tangent, you are correct. You would say the tangent of 75 degrees is equal to the opposite side of x over the adjacent side of 300 feet. And just like the last one, you would have 300 feet times the tangent of 75 degrees equal to x. And if I type that in my calculator, 300 times the tangent of 75 degrees, we get that the height of the cloud was 1,119.62 feet. Just do that here. So x was 1,119.62 feet. There you go. Okay, so just drawing your diagram helps, unless you're given diagrams and it's not bad. All right. And last one. This is a fun one. Find the exact value of the cotangent of 1 times 2 times 3 times the cotangent of 89. So in your calculator, type all of that to 89. Just kidding. No, that's too much. To simplify this one, to solve it, we are going to use complementary angle theorem because that's going to simplify things. So, using the cat, we know that the cotangent of theta is the same as the tangent of 90 degrees minus that theta. And using identities, we know that cotangent theta is the reciprocal of tangent. So this is known as 1 over tangent theta. And therefore, if I said cotangent theta times tangent theta, you would get 1. So let's use all this information to help us solve this one. So let's examine the cotangent of 1 degree, meaning let's use complementary angle theorem. So the cotangent of 1 degree using complementary angle theorem will become the tangent of 89 degrees, which means that tangent of 89 now replaces the cotangent of 1. So if I wrote that again, where's the best way to write it? Let me see. So you would end up getting tangent of 89 times cotangent of 2 times cotangent of 89. So since they're all connected by multiplication, you probably see what's going on now. This tangent of 89 and that cotangent of 89, using this example, will cancel and become 1. So this means tangent of 89, cotangent of 89, cancel. Tangent of 88, cotangent of 88, cancel. 70, 87, 86, 85, all the way till you get till the middle term of, because everything is going to cancel, and you will be left. Let me see. What's the best way to write this? Can't write today, I'm sorry. Maybe I'm just so excited. Those will cancel and become 1, and all that's left is the middle term of the cotangent of 45 degrees, which also happens to be 1. That's it. So it's like one big cancellation fest. Cancel, 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 until you get to the tangent of 45, which is 1. And we are done. Whew. There you go. Now you know how to call a unit circle. You know the coordinate values on the unit circle. I'll fill them out after I'm done with this video. And that's it. Nothing to it. Triangles are life. So see you at the next one.